We're back. So it's been a hot minute since we last talked. But I assure you I have a perfectly good explanation for my absence. I was busy and I didn't feel like making YouTube videos. But I'm trying to get back into the swing of things here, and I figured I'd make good on a video I said I was going to do probably about 2 years ago now, which was tuning a Motorola preselector. So these are a super common piece of equipment. You see them on all kinds of Motorola repeaters. The MTR 2000s and 3000s have them. The Quantars have them. They're vertical, kind of shoved back in to the receiver section. Hell, the GTRs might even have them. And they're ubiquitous in the RF world. They're a cavity bandpass filter. The UHF one, which this one is, has 3 cavities, 3 tunable cavities. The VHF ones, which are 5 cavities, you see there's 2 extra holes here that aren't used. They use the same casting. The VHF ones have 5 cavities. That's just to get a little bit tighter skirts on the bandpass filter in the VHF band. Brian Fields, W9CR, his wiki has a really good teardown on these preselectors, what's inside of them and the performance that you can expect from them. So I'm not going to get too into the weeds of how they actually work. I'm just going to tell you my use case for this filter and how I'm going to tune the thing. So the first question is, of course, what is a preselector? Well, in this case, a preselector is a filter that you put in front of your receiver, your radio's receiver, and the goal is to make it a little bit more sensitive and to block out a little more unwanted signals outside of your receive band. So at a lot of repeater sites, you know, you have all kinds of different transmitters transmitting on all different frequencies. You got mixing products to deal with, intermod products all over the place. And to make sure that you have the best fighting chance you can get to receive the signals you want to receive, especially the weaker signals, you put a preselector filter in front of your radio's receiver. And it's basically just an extra filter, an extra bandpass filter that is tuned to a more specific frequency band. So for instance, you know, the UHF R2 Quantar covers 430 to 470 megahertz. And this filter is about 3 or 4 megahertz wide. So, you know, if you've got a frequency of interest up at 450 megahertz, you tune this thing to be a smaller little chunk of that spectrum, and it filters out everything else, and in theory lowers your noise floor and makes your weaker signals a little bit easier to receive. So I'm a visual person, so we're going to get out the pencil and paper. I'm going to draw a little diagram for you here. So let's say this is the bandwidth of your radio. You know, 430 megahertz is down here, 470 megahertz is up here, and that's a really wide chunk of spectrum. You know, the ham band is all in through here, and you got your commercial stuff up through here, and there's all kinds of little sub bands in there for different areas, and you want to receive a signal right here. This is the frequency of interest, let's call it 460. Note, this is not to scale. Well, by default, your radio's receiver is going to be receiving every single signal within this entire bandwidth. There may be some, you know, tracking filters and things built in to try and tighten it up a little bit, but essentially, your radio connected to the antenna is going to hear every signal from 430 to 470 megahertz, and that's typically not ideal, especially if you're in a urban area that has a million different radios and a million different repeaters up all over the place. You're going to be getting a lot of other transmitters interfering with your reception, especially if your radio signal here is a lot weaker than a neighboring transmitter there or down here. You know, these two might be 10, 20, 100 times more powerful than the really weak receive signal you're trying to receive, and they're going to be blowing your receiver out of the water. So in order to try and combat that, you use a preselector. What that essentially looks like in practice is, if this is that same span of frequencies, instead of receiving everything across that whole band, your filter cuts out most of it, and you tune it so that it has just a little skirt right up here, and then it cuts back off on the other side, and you're filtering out everything you don't want to hear. So now you've still got the signal you're trying to receive at the same power it was before, or maybe minus a dB because the filter is going to have a little bit of loss. But these two big guys on either side are going to be way attenuated, so they now look like that. It's going to be way easier to receive that signal of interest. So now let's talk about what I need this preselector for. I have a super secret project that I've been working on here in the lab. I'm hoping to make a bunch more videos in a big series about it. It's something really, really cool, and something that I'm hoping to show at Hamvention next year. But it is a 4-channel radio system. It has 4 independent repeaters, all running into a common set of antennas. So I have 4 frequencies that will be transmitting and 4 frequencies that will be receiving. And I need to make sure that the receive frequencies have enough filtering that the transmitting frequencies don't just blow those receivers out of the water. So it's the same general idea as what I was showing here, just a little bit different use case. So in my situation, I've got 466.0625 to 466.2875 megahertz. Those are my receive frequencies. And I'm using a standard 5 megahertz offset, so my transmit frequencies are going to be 461.0625 to 461.2875. So I need to filter my receive frequencies enough that my transmit frequencies aren't going to get in the way. So we're going to do a little bit different tuning. You know, normally with these filters you would tune right into the center. So, you know, right in the middle of this passband would be where your center frequency would live. I'm going to do things a little bit differently for 2 reasons. One is, if I were to do this, the bandpass filter is only about 3 or 4 megahertz wide. I would start to be bleeding in, if I draw a little bit better here, the curve's more like that. If I tuned right in the middle of my 4 frequencies, down here would be my 4 transmit frequencies, and you can see I'm not getting as much attenuation as I could be from those signals. So what I'm actually going to do is deliberately tune the center of this filter higher in frequency than my actual receive. So if this is my transmit, this is my receive, and I'm drawing them like this as single spikes because they're so close together. You know, if you zoom out enough in the spectrum, they're going to look like single spikes essentially. So what I'm going to do to tune this filter is actually tune it so that the passband edge just hits the edge of the receive frequency like that. So it's on the lower edge, but that should mean that I'm getting the most attenuation on my transmit frequency that I can be. So that's a pretty common use case for these preselectors. I'm not doing anything crazy radical here. And this should be a fairly straightforward and simple video. I'm just going to show you the way I tune these preselectors. It's a little bit different than how Motorola recommends you do it, but I find it works better for me, and it's typically a lot faster and honestly a lot more precise. So let's talk about how you tune these things. Motorola has a standard tuning procedure for these filters. You can find it on the internet. It's pretty easy to get a hold of. And it dates back from a time when not everybody had a vector network analyzer available. So it does things a little bit differently than you might expect. The way they tell you to tune these filters is to use a reference transmitter going in one side and a little RF probe. It's just a basically a little tube with a needle probe at the end of it. And there's these little cavities next to each tuning rod. You can see them here. What you do is you would start transmitting your reference signal, and you would hook this up to a power meter or an oscilloscope or whatever you wanted, and you'd stick it into each of these little holes, and you'd individually adjust each of these tuning slugs until you got maximum power at the frequency you were interested in. So that works. That's a totally valid way to do it, and that will make sure you're minimizing the amount of loss through the filter, but it doesn't necessarily mean that your bandpass is perfectly where you want it to be. All this really tells you is that your receive frequency is going to pass through the filter optimally. So that's a totally valid way to tune these filters, especially if you don't have access to a vector network analyzer. Sometimes it could be the only way that you can tune these filters, but I'm going to do it with access to the test equipment that I've got. So instead of using a reference transmitter and this probe, which I don't have and which are expensive to buy online, I'm just going to hook one end into port 1 of my vector network analyzer and take the output into port 2 of my vector network analyzer, and we're going to measure the S21 response. So if you're not familiar with S parameters, that's a whole nother video I could do, and there's plenty of other people who've done much more informative videos on S parameters and measuring them with vector network analyzers. But all you need to know is that S21 measures the amount of power received at port number 2 from port number 1. And you measure that over a frequency sweep, and you get a nice little plot showing the response of the filter you're tuning. So now it's time to introduce a new character here in the lab. I actually got this piece of test equipment probably a year and a half ago now, but I just haven't made a video using it up until this point. This is an HP 8712. It is a vector network analyzer that goes up to 1.3 gigahertz. It's the little baby brother of the HP 8714, which goes up to 3 gigahertz, and that's the same vector network analyzer that IMSAIGuy has on YouTube. Another great channel, by the way. Absolutely go check out his videos and subscribe to him. But I find that for what I do here in the lab, 1.3 gigahertz is plenty high enough for me. I'm very rarely ever even approaching 1 gigahertz, let alone ever needing to go up to 3 gigahertz for now. We'll see if that changes in the future. I might get into a big microwave kick here, you never know. But for now, most of the radio stuff I do is well below 1 gigahertz, and this VNA is going to do the job just fine for me. So let's go ahead and power them up. It is old, early 90s technology, so it's got a classic CRT and does take a while to boot up. But as far as I can tell, it seems to work great, and I've been using it non-stop here since I got the thing. Fantastic investment, and I did, as usual, get a pretty good screaming deal on it. So this is one of the annoying things about these pre-selectors. They have two mini UHF connectors on them. Motorola loves mini UHF connectors. Almost every radio they've made, pretty much up until the Apex 8500 had mini UHF connectors. And they point at each other, so if you wanted to use straight RF adapters, you'd see they'd eventually run into each other. So you either have to use custom test cables that have right angle mini UHF connectors on them, or you do what I do and play adapter palooza here until you get to normal SMAs like the rest of the world uses. And these are just mini circuits SMA test cables. I got them off of eBay for about 30 bucks each. They're not, the fancy phase stable, super expensive Megaphase or Gore RF test cables, but again, we're working below 1 gigahertz here, so you don't need all that fancy stuff unless you just want to show off. All right, so the first thing we're going to do here is set up our measurement. Now, I apologize, I did not get the 8712 ET, which is the modernized version of the 8712 that has a VGA output that I could easily screen capture. I think it also has a built-in web server, which is fancy stuff back in the mid-90s. But this is the older version that doesn't have any of that. I think it's got some weird kind of composite output that no capture card understands, so instead of trying to futz around with all that, I'm just going to record the screen and you're going to have to live with it. But that's enough ranting. Let's go ahead and set up our measurement. So first thing we got to do is set our start and stop frequencies. For rough tuning, I'm just going to go ahead and go, let's do a center frequency of 460 megahertz. And we'll do a span of, how about 10 megahertz to start with? That should get us close. We're already in transmission mode here, which is good. If we wanted to change that, we would change our channel measurement here. We could do reflection power, other interesting things that we don't need to worry about today. But I do need to calibrate our test setup. The easiest way to do that is just to normalize it with the normalize button. So all we need to do is connect our two test cables together and hit that normalize button. Now this isn't 100% accurate because technically we do have a little bit of extra loss with those adapters we're using, but I can almost guarantee that would be probably less than 1/10 of a dB, and for what we're doing here, pretty much insignificant. So we've got our cables connected together. We're just going to hit the normalize button, and you'll see we now have a nice flat line along the top of the screen here, reading 0 dB across the board. That means, since we're measuring transmission loss, or what we call insertion loss, that means between our two test cables, we have 0 dB of loss across our frequency range. And that's to be expected because they're connected directly together and should have no loss. So I'm gonna go ahead and hook these up to the filter we're trying to tune here. And assuming this thing isn't way off frequency, we should see at least part of a curve, if not a whole curve, show up. I think a lot of people freak out about measurement precision and adapter losses I'd love to do a video sometime comparing adapters, but you know, adapters, they do add loss, and if you have enough adapters at a high enough frequency, you will start to see an actual significant impact in whatever you're doing. But honestly, I think the adapter discussion is pretty overblown 90% of the time, and you really shouldn't be afraid to use adapters, especially if you're getting them from, you know, not some random Chinese seller on eBay. They should be good enough for what you're trying to do. But anyway, here we go. We got the filter hooked up, and we see a slightly curved line. So what this tells me is that the actual peak of our filter is probably way over here somewhere, way lower in frequency. So we'll go ahead and just zoom out until we can see it. Let's bump out to, I don't know, 50 megahertz to start with. There we go. That's what I'm expecting to see. So let's see. Our peak of the filter is actually tuned to about 440, 445, 443-ish megahertz. So this was probably used as a receive filter in a ham repeater at one point in time. But we're going to go ahead and set our marker to our frequency of interest, which I'm just going to say 466 megahertz for now because that's close enough. And let's start tuning. So I should probably caveat before we get started here that there are a million different ways to tune cavity filters. Everybody has their favorite way. I'm sure they're all going to tell me I'm doing it wrong, and my response to that is, well, so are you. It doesn't really matter how you tune these things as long as you get the performance you want out of it. You know, properly tuned, you can get less than a dB of insertion loss on these things, and that's what I'm going to shoot for today. But, you know, if you can get it tuned and the loss is acceptable and the response is acceptable, then for your purposes, it's tuned. It may not be tuned perfectly or exactly how the engineers wanted it to be tuned back in the 80s when they designed the thing, but personally, I don't think that really matters all that much. Feel free to disagree in the comments. And one other thing I should probably clarify is this is not technically a true cavity filter because there's more than just a cavity inside each of these sections. A true cavity filter is something like a duplexer where you have a big, huge can that's just a resonant cavity. These are a little more complicated than that. Again, Brian Field's wiki that I'll link down below has a awesome teardown and tuning instructions for these things on how to actually switch them between bands. And it goes over the construction and how they actually work. It's really kind of a discrete capacitor inductor design and lets it be a lot smaller than a similar sized duplexer would be. Obviously the performance is not going to be as good as a full size duplexer, but it's not a duplexer, it's a pre-selector filter. So anyway, that's enough rambling. To tune this, you just have 3 adjustments, one screw for each of the 3 cavities, and you crank it in to move the frequency one way and crank it out to move the frequency the other way. I like to use these tweakers. You can get these pretty cheap on Amazon or eBay or wherever. These are no-name, no-brand tweakers. It's essentially just a ceramic rod with a screwdriver flat ground into it. You can get it with Phillips heads as well. I've got one of those here somewhere. Yeah, you can get it with Phillips heads as well. These are useful for tuning things where you don't want conductive metal to get close. It'll throw off whatever you're trying to tune. I'm not sure that really matters in this case, and these are really easy to break, and if these screws are stiff enough, it might actually break the ceramic bit, and I might just move to a standard screwdriver. But if you're tuning really, really sensitive circuits with where the capacitance of the screwdriver going in there would affect things, these are really handy to have. I've got a whole bunch of them sitting up in my tool rack. So like I said, I don't have a good way to record both the VNA and what I'm doing here at the same time, so I'm not going to record what I'm doing over here with the filter itself. It's just going to look like this. I'm going to have a screwdriver in there, and I'm going to be turning it one way or the other to change the frequency, and that's really all you need to know. It's not complicated stuff. So let's get started. Now, tuning any filter like this can be a little finicky. Basically, as you adjust one of the cavity sections, it's going to change the resonance and change the tuning of the other sections. So once we get closer, you're going to find yourself kind of going back and forth between the 3 different rods and kind of fine-tuning and tweaking until you get things where you want. It's just the nature of how this works. Like I said, everybody's got their own way of doing it. My way is just look at the graph and move things around until you get it where you want it. So I was turning the first screw in, and you can see that was moving that part of the response down. So I'm actually going to turn it out the other way. We're coming up, And you can see that it's slowly shifting up in frequency. You're going to probably eventually see two distinct humps starting to form. Yeah, there you go. So what you're seeing here is this is the response curve for the cavity I'm tuning right now, and this is the curve for the other two that haven't been tuned yet. Eventually we'll move those other two over to here as well, but I'm getting this first one kind of close to where we want it to start with. So about there is good for now. And we'll move the other two over to do the same. And you can see you can get some really interesting curves as you're doing this, where those filters are kind of fighting each other and way off frequency of each other. You can see it really hurts your insertion loss, because like right now, I've got two of the three about where we want them, and you'll see we still have about 14 dB, almost 15 dB of insertion loss there, which is really terrible. When these things are tuned properly, you can get it under a dB easily. So now, when we do the last cavity here, we should start to see everything starting to look a little bit better. And as I move this up, you'll see our response gets a lot closer to what we expected it to look like, and that insertion loss also goes way down. So it maxed out there, or I guess minned out there at about 1.1, 1.2 dB of insertion loss. And we can get that better, but I'm going to go ahead and zoom in here so that we can see what we're doing a little bit easier. So I'm going to punch the span into maybe 10 megahertz. That might be a little too close. We'll see. Yeah, we'll go out to 20. And I'm going to change the scale as well from 10 dB to 5 dB per division. That's just going to move up the scale that way a little bit and let us see what we're doing a little bit more. And the last thing I'm going to do is put another marker at 461 megahertz, which is, if you recall, where our transmitters are going to live and where we want to start trying to block some of that frequency. So now it's just a matter of fine-tuning things, and I'm just going to go back and forth between the three different cavities here. What I'm trying to do is shift this curve over as much as possible before it starts impacting our receive frequency area, to try and get as much attenuation on our transmit side as I can. Now, if you were trying to do something like run your transmit and receive into a single antenna, this would not even be close to enough filtering. That's when you would use an actual duplexer, and those have a combination of bandpass and band reject cavities, and that lets you get, upwards of 80, 90, 100 dB of isolation between your transmit and receive frequencies, and that's what lets you actually combine those both into a single antenna. We're not trying to do that here because I'm going to be running these on two different antennas. I'm going to have a separate transmit and receive antenna, so we don't have to be nearly as tight, but I am still trying to get as much rejection as I can, because that means I don't have to move my antennas away from each other as much, and it just means the system's going to perform a lot better overall. So I'm actually going to zoom in even a little bit more now that we've got it kind of where we want it. I'm going to change my center frequency to, let's say, 463 megahertz, and zoom in even a little bit more on the scale. Maybe go 3 dB per division. There we go. Now we're talking. And yeah, just doing the same thing, moving those rods in and out to try and minimize marker number 2 there while maximizing marker number 1 there. And I'll go back to our marker display there so you can see the individual values. And this is kind of the balancing act that you play, trying to adjust all three cavities to get a good balance of rejection and insertion loss. It looks like about 1.3 dB is going to be where I end up. I could probably make that a little bit better, and I'm going to try to tune it in here as much as I can, but again, to really get that minimum amount of insertion loss, I would have to move kind of the center of the cavities over here, and when I do that, it's going to bump up the or reduce the amount of rejection I get at the transmit frequency, which I don't want. So 1.3 dB of insertion loss and 17.5, almost 18 dB of rejection on a transmit frequency. That's not terrible. That's about what I expected this to look like going into it, but I'm just going to keep playing around with it here a little bit and see if I can't make it just a little bit better. And I'm going to stop there for now. I think that's about as good as I was looking to get. You'll see I'm actually getting a little bit of a double hump in my passband there. If we zoom out a little bit, you'll see what I'm talking about. And that's kind of what you see when you don't have all three of the cavities at the same exact frequency. I've got probably two of them resonant right around here, and the third one is resonant up here. That's actually helping me in this case because you can see that after the little hump here, the rejection notch is pretty sharp there. And if we go back to our markers, we'll see I'm getting almost 20 dB of rejection at the transmit frequency there. Insertion loss is about 1.5 dB. That's not amazing, but that's also not going to be super impactful to the system performance. You know, that might limit the range at the very fringe of the system, but without revealing too much about this system, it's going to be a portable, deployable repeater system, and 1.5 dB of extra insertion loss on the receive chain is probably not going to be a huge deal. If I really wanted to go crazy, I could probably add in a preamp after this pre-selector filter to try and bump up the receive signal a little bit more, but that's overkill, and that opens you up to all kinds of extra issues with, you know, distortion in your receive chain and overloading it from your transmitter and a bunch of extra things I just really don't want to deal with. So I'm going to call this good for now. We'll zoom out a little bit more in our scale just so you can see kind of what it looks like. There's the filter response as we expected it to look like, and that's really all there is to it. And you can see this is where our 3 tuning screws ended up after the tuning. They're sticking out significantly farther than they were at the start. That's because we have essentially shortened the inside capacitor inductor assembly, which raises the frequency. And yeah, that's really all there is to tuning these things. You'll notice I switched over to a standard metallic screwdriver. That's because A, it wasn't really affecting the tuning all that much. I can touch this all over the thing and I don't see that response curve move at all. And B, I already broke a couple of these tweakers because these are pretty stiff tuning tubes, which we would hope they are. We don't want them changing on us while the thing is, sitting in the repeater and shaking around and vibrating. But yeah, those little ceramic tweakers, not exactly the best tool for tuning really stiff tuning rods like that. So there you go. Super short video. I am trying to be a little bit more regular with the content uploads. I have lots of different ideas in my head for videos I could make. It's really just getting over my laziness and actually shooting them, editing them, and uploading them. Like I mentioned earlier, I do have this new big project kind of on the horizon. I've already started building the thing. It's more just a matter of recording videos and actually showing off all the different parts. But hopefully you found this fairly interesting. And I guess stay tuned for more videos. With any luck, the next one won't take 11 months to get out. Thanks for watching. Talk to you guys later.